You know, every time you shop online, send a message, or even just check your bank account, you're trusting some hidden technology to keep you safe. Well, that technology is encryption. But here's the thing, it's not just one magic trick. It's actually a clever combination of two different methods. And today, we're going to unlock how they work together.
We all do it, right? We look for that little padlock in our browser before we type in a password or a credit card number. It makes us feel safe. But how does it actually work? Well, behind that simple icon is a really sophisticated exchange of secret keys. And that's exactly where our story begins.
All right, let's start with the most straightforward idea. Imagine you have a secret diary and one single physical key. You use that key to lock it, and anyone who wants to read it needs that exact same key to unlock it. Simple, right? Well, that's the core idea behind what we call symmetric encryption.
The name pretty much says it all, symmetric. It's balanced. Just like with that diary, the key that locks the information is the very same key that unlocks it. So for this to work, both the person sending the message and the person receiving it have to have an identical copy of that one single secret key.
Now, this single key approach has a huge advantage. It is incredibly fast. That efficiency makes it perfect for heavy-duty tasks, like encrypting your entire hard drive or securing a non-stop video stream. But it has a massive, glaring weakness. If you and I both need the same secret key, how do I get it to you in the first place without someone else intercepting it?
Okay, don't let the formula intimidate you. All this is really saying is, to get your original message, which is P, you have to decrypt D, the scrambled message, using the exact same key, K, that was used to encrypt E it. See? The key K is used on both sides of the equation. It's clean, it's simple, but that simplicity is also its biggest flaw. And this, right here, is the million-dollar question. It's known as the key exchange problem. I mean, you can't just email the secret key to your friend. If someone intercepts that email, they have the key to everything. It's like mailing the key to your house in a clear envelope. This single problem paved the way for a completely different approach. So, to solve this really dangerous key sharing problem, cryptographers basically flipped the whole idea on its head. They asked, what if you didn't need to share the secret key at all? What if, instead of one key, you had two different keys that worked together as a team?
This is where things get really, really clever. Instead of one key, you generate a mathematically linked pair of keys. One is your public key. You can post it anywhere, give it to anyone. It's not a secret at all. The other is your private key, and that's the one you guard with your life and never, ever share. So here's the crucial part. Anyone can use your public key to lock a message and send it to you. But once that message is locked, only your private key can unlock it. This solves the key exchange problem beautifully. The trade-off? Well, it's much slower and requires a lot more computing power. That's why it's used for things like authenticating identities and securing those initial connections, not for encrypting massive files.
The formula here really shows the magic. So anyone can use your public key, Q, to encrypt a message, P. But notice, that public key cannot unlock it. The only thing that can decrypt it is its other half, the completely different private key, KD. They are a matched pair, but the lock and unlock functions are totally separate.
Okay, so we've got two powerful methods. One is lightning fast but has that dangerous sharing problem. The other is incredibly secure for sharing but is slow and, resource heavy. So let's put them side by side to really see the differences.
This table just lays it all out perfectly. First thing you'll probably notice is the speed. Symmetric is fast, asymmetric is slow. And that's why one is for large data and the other is for small amounts of data. But why is it so much slower? Well, take a look at the key length. To get the same level of security, an asymmetric key needs to be almost 10 times longer. And that right there requires a lot more computing power, making it way more resource intensive.
So, which one is better? It kind of feels like we're stuck in a classic speed versus security dilemma, doesn't it? But what if we didn't have to choose? What if the smartest solution was to just use both?
So how do you choose? I mean, think about it. If you need raw speed for a huge file, you'd pick symmetric, no question. But if your absolute top priority is safely establishing a connection without anyone stealing your key, you'd have to pick asymmetric. And this very trade-off leads to the brilliant solution we all use every single day.
So what's the answer? The solution is to not choose. It turns out the most secure systems on the planet don't pick a side. Instead, they brilliantly combine the two, getting the absolute best of both worlds.
This is precisely what happens when you see that padlock icon. First, your browser and the website perform what's called a handshake. They use that slow but ultra-secure asymmetric encryption. And its only job is to do one tiny thing: safely agree on a brand new temporary symmetric key. Once that key is created and securely shared, they switch. The rest of your session, all the images, the text, and the data, is protected using lightning-fast symmetric encryption. It's the perfect partnership.
You know, this isn't just theory. It's the invisible engine of trust for the entire internet. It's what protects your banking, your emails, your private messages. So the next time you see that little padlock, you'll know the secret. It's not one lock, but a brilliant two-step dance of protection. And that kind of makes you wonder, where else is this silent protector at work for you right now?